Hey everyone, my name is Korbonits and I'm a data scientist at Remitly. This talk, which is kind of just the opener talk, the opening band, if you will, for TED, is broadly about evaluating and comparing machine learning models. I'm going to talk to you about the practical problems of model selection in the context of machine learning-based classifiers, specifically, and how in today's literature, model selection is sort of glossed over, not really talked about too much in depth, but I'm really going to go into some of the practical concerns looking at economic costs associated with machine learning models and looking at things like class and balance a little bit. Basically what I'm trying to say is that if you're using machine learning in practice, in an industry setting, you want your models not just to make sense, but dollars and cents. But before we dive in, here's a little bit about Remitly and me. Remitly was founded in 2011 to forever change the way people send money back home to their loved ones and their family members. And we're taking off strong right now. There's currently over $600 billion sent abroad in the form of remittances worldwide, which is about 4 times the total amount of foreign aid and nonprofits sent across the world. So that's a big chunk of money, and we're now the largest independent digital remittance company in the United States, which is pretty cool. We just announced our Series C in April, and we're now sending, I just queried this morning actually, over $1.4 billion annually around the world, and only growing from there. Something exciting happened last Friday. Our CEO, Matt Oppenheimer, just got named Ernst & Young's Entrepreneur of the Year, which is pretty great in the services category. So we've got good leadership and excited about what's coming. More about me. I'm working as one of 2 data scientists on our data science team at Remitly. Maybe one of you will want to be our third. If that's interesting to you, please feel free to come talk to me afterwards. Sounds great. I'm proud, born and raised Seattleite. Woo! How many of us here are from Seattle? Yeah, all right. I feel just proud of where I'm from, and always like to point that out. As Al said, I'm an organizer of DAML as well, and I've been a data scientist previously at another startup in Redmond called Nuku. Fantastic. So the agenda for this evening's talk, just want to give you guys a brief outline, and I'll go quickly through this. We're going to talk about model selection and why data and fancy algorithms are not the only knobs you have when it comes to solving your machine learning problems. This is hard, and we've been finding that traditional approaches are inadequate. ML algorithms themselves have had a lot of academic coverage. Model selection problems haven't had quite as much of a focus. So this aspect is crucial for us in terms of delivering successful data science applications. A couple of these problems include the inclusion of economic constraints and class imbalances in the model selection process. For us, there's a real penalty in being incorrect with our classifications. We have very high costs of misclassification in the form of type 1 and type 2 errors, for example. After that, I'm going to talk about how to address the economic impact of model selection, how to incorporate these different costs, just kind of at a high level. And then I'll touch on why not only this matters to us, but just emphasize that we're just getting started. As we like to say at Remitly, we're just getting started, we're not done yet. There are a lot of exciting things ahead of us. So you may think that in order to solve all of your machine learning problems, you only need to have big data. Or maybe you think all your problems will be solved with deep learning and neural networks, all these awesome buzzwords lately. Even Silicon Valley, the TV show on HBO, has been dropping neural networks and machine learning like it's nobody's business for the last few weeks, which I think is hilarious. But I will say, please stop fanning the flames of AI hype before another AI winter sets in. Thanks. So, like I was saying, it's not the case that you can use big data and deep learning to solve all of your machine learning problems. You really need to think carefully about model evaluation and comparison. So how do you do this for your use case? How do you evaluate and compare models in your specific setting outside of studying the theoretical properties of an algorithm? Today we're just going to focus on model evaluation in a supervised classification setting, specifically binary classification, in the context of fraud classification. Just to give you a little context. So for us, big data is not enough. Not everyone has it, first of all, or maybe what you have isn't that useful. And fancy algorithms aren't a silver bullet either. You know, the no free lunch theorem, as we know, tells us that there isn't a one-size-fits-all learning algorithm for any given classification task. So for all you deep learning people out there, beware, here be dragons. Model selection is tough. There isn't a lot of coverage in literature. It's a very practical problem, and it matters to us tremendously in our day-to-day work classifying fraud. So how do we do it? What do we need to incorporate so that we can improve the approaches we've been seeing thus far? It's not just about, you know, cross-validation, things like that. We're not just going to be comparing different classifiers endlessly and seeing which ones have the best performance. No, we need to have sort of an objective external standard by which we pick a model. Basically, we want to tie models into our business objectives directly. So in econ, there's this notion of indifference curves and utility. You may have a problem, like fraud classification, where the penalty of misclassification varies per instance. It's not sufficient to have, say, a loss matrix while training an algorithm so that you can weigh the penalty of misclassification higher for a different class. Each transaction instance can have a much higher penalty than another. For example, you may have transactions with several orders of magnitude higher send volume than another one. And so you can't have a single matrix represent the penalties across all of your transactions. So that's not really what we need to do. In economics, you know, we have budget constraints and utility functions. Rational individuals, homo economicus, if you will, we like to maximize your utility by achieving the highest curve we can given our budget constraint. And so each point along this curve is equivalent in terms of trade-offs. It's called indifference curve, or maybe another term that people are familiar with would be a level set. Again, like I was saying, we have transactions, we have revenue associated with these transactions, but we also have costs. There's cost of review for reviewing a transaction unnecessarily, it's fraudulent, or that we think is fraudulent. And there's also the cost associated with missing a transaction that's fraudulent. And that's the highest cost of all. All right, so now that everyone's up to speed on economics, this is a confusion matrix. Confused yet? Models that have to predict a propensity score, such as logistic regression, have trade-offs. So it's not really one classifier. It's sort of a continuum of classifiers that you can choose as you vary your threshold of classification from 0 to 1. And what do I mean by that? When you have a model like logistic regression, you output a probability for your prediction. And basically, if you pick, say, a threshold of 0.5, you create a confusion matrix. Basically, you vary the threshold and you can create a continuum of different confusion matrices for your problem. So there isn't really only one you have. When you're working with models that allow for you to make trade-offs, you have to think about which model gives you the best confusion matrix, if you will, for your problem. So we have to look at all possible confusion matrices that our model can help us achieve, and then pick one there. So how do we do that? Well, one of the classic ways is my curve is better than your curve. Therefore, I'm going to publish this ML paper and call it a day. This is the receiver operating characteristic curve, or ROC curve, which was originally used for detecting enemy objects in battlefields in World War II. It's pretty cool. This is one of the most prominent metrics for comparing and evaluating machine learning models. It's useful, it's impervious to class imbalance. It's common in the literature as well as in many fields like psychology, social science, and of course, machine learning itself. Basically, this dashed line, for those of you who aren't familiar, is the sort of x equals y line, and this represents what a random classifier would predict. So in other words, where the true positive rate on the y-axis would equal the false positive rate on the x-axis. One of the problems with this curve, even though I was saying it was a benefit earlier, is the fact that it ignores class imbalances. That's important for your problem. Another issue is that it ignores the costs of false negatives and false positives, which you may want to incorporate. Another very common and important machine learning metric is precision and recall. This is a little bit different than receiver operating characteristic. We have recall, which is the same as the false positive rate here, usually on the x-axis, and precision on the y-axis. So recall you can kind of think of as, of all the positive instances, what proportion of those did our model classify as positive? Precision, the wording is different, and it's important that it's different. Of the positive classifications that your model has made, what proportion of your predictions had positive ground truth? And so this curve is sort of, again, just like the ROC curve, a set of trade-offs at which you can pick a point and determine the confusion matrix that would result from using that threshold for classification. So we haven't talked about cost yet. Let's do that. It's all well and good that one of my PR curves is better than another, but what if they're similar? Can I have a precision and recall curve or a ROC curve with worse area under the curve that actually suits my needs better? Generally we think, oh, the ROC curve with the highest area under the curve is the one I want. But I'm going to kind of turn that around and suggest maybe that's not what's right for you. Here's an example in ROC space. We've got two models, and we've got an indifference curve that we've created based on the costs of misclassification. So in each quadrant or confusion matrix, you have different costs. Your costs will define basically the slope and intercept of this line. And again, look at the orange one. The orange one has higher area under the curve, but the green one actually crosses our indifference curve. Why is this important? It means that this orange model is not viable for your business. It means that you may be losing money. Whereas the green one may have like lower AUC or worse predictive performance at thresholds below where it intersects with the orange predictor. But what matters is that it actually achieves thresholds in the space of this chart that are above your indifference curve. In other words, using thresholds on the green line here allow you to maximize your profit or expected utility, or whichever way you want to phrase the function with which you are computing these indifference curves. And I just want to make a quick note that indifference curves don't need to be linear. One other thing, last in this talk, I'm not going to explore weighting training points differently during training or different resampling methods. These metrics that we're talking about with indifference curves are sort of post-training. Here we want models that output propensity so we can pick our own thresholds. And as mentioned previously, loss matrices during training do not work for our use case because of the transaction issues. So let's go back to PR space. We've got a machine learning metric that we've chosen to evaluate the predictive performance of our models. We've maybe got two models that we want to compare to each other and pick one maybe better or worse than another. We've got business costs, business objectives, constraints that we are subject to as a business, and we've got all those things together. Now, how do we actually pick a model? So here in precision recall space, we've got an indifference curve and two models. Note that the curve in red, which is your curve, has worse area under the curve in this space than my curve, which is the blue curve. But what matters is that your indifference curve here is pretty extreme, and all points to the right of that suggest that the red curve, which is yours, actually dominates the blue curve in terms of its maximum distance perpendicularly from the indifference curve. So that threshold is the point at which you are sort of maximizing the utility of your constraint. This is sort of the point you want to be picking on this curve based on your own indifference curve. So this kind of is counterintuitive when you are used to thinking about comparing models in terms of the area under the curve, or looking at one curve strictly dominating another in PR space or ROC space. One thing to remember, if this is an approach that you're thinking of using, be sure to remember that business objectives and costs change over time. So you'll want to constantly recompute and reevaluate what these indifference curves look like so that you're sure that when you're training models and looking at the model selection process, that you're actually choosing models based on the current economic reality. Great, so precision recall and receiver operating characteristic are obviously not the only metrics that are useful or important or interesting when you are evaluating the selection process for your models. So I just wanted to bring up a really great talk that there's a link to in the bibliography. Sam Steengold gave a talk at the ML Conf in Seattle in May that I thought was really awesome. He talked about different machine learning evaluation metrics, and there are 4 that are plotted here across their different ranges, basically to show you just how they behave. He talked about accuracy, which we're all familiar with, the F-score, one that he called Pearson's fee, which I call Matthew's correlation coefficient, which is a pretty balanced metric that works well with data sets that are balanced or imbalanced. And another metric that is called proficiency, sort of an information theoretic metric that helps you understand how well your model is explaining the information contained in the data set. So one interesting jumping off point from this talk would be to evaluate the notion of incorporating indifference curves with these other metrics in their respective spaces. So briefly, we talked about model selection. Data and algorithms aren't the only knobs you have. You've got a lot of knobs to turn in the data science process, and you can use other knobs such as your costs and your revenues to be able to do model selection. We talked about some of the problems with typical model selection processes. Some of them are just inadequate to help you out with solving all of the problems you need to solve. We looked at precision and recall and receiver operating characteristic and fusion matrices. We also addressed the economic impact of model selection and why this is important. Because if you have a model that doesn't even hit your indifference curve, you don't have a viable model. You need to keep going or reevaluate the model creation process or even the costs and revenues that you can achieve. Last, this matters to Remitly a lot because we are operating in a pretty constrained space. We're in a very competitive landscape. We're price takers in that competitive landscape, so we can't adjust our prices very much. Our costs are high. There's an extreme imbalance in cost between the revenue associated with a successful transaction and the cost associated with a fraudulent transaction. So we have to be very careful about how we build models to classify fraud. So what does machine learning look like at Remitly as a whole? On the data science team, we're currently using machine learning for a variety of purposes, but here's a really important point. Machine learning applications are core to our business. Therefore, our business has to be core to our machine learning models. This is the driving force behind how we're doing model evaluation and comparison at Remitly. More specifically, we're using ML for a few other applications. As I said, fraud classification, left swipe on fraudsters, right swipe on great people. We're working on anomaly detection, stopping money launderers in their tracks. More of a marketing perspective, we're learning why users love using Remitly, why they keep coming back. Should we make changes in the product to increase retention and reduce churn? And last, because we're operating in a financial landscape, it's really interesting to look at movements in currency markets and see how that might affect demand of the app. So a lot of exciting things going on, and we're just getting started. So thanks so much.